Okay.
Okay.
I think we can start now so that we have the time and there is some time for questions at the end of the talk. So thank you everybody to be here with us with our brand new series of seminars organized by Ithaca, Italian Category Theorist Network. And our first talk is by Pierre-Alain Jacqmin from the Royal Military Academy in Belgium, I suppose.
Yes.
So the talk title is Surjection-like Classes of Morphism. Thank you very much. Pierre-Alain, it's to you.
Okay, thank you very much, and thanks to all the organizers for the invitation to speak in this seminar. It's a real pleasure. And before to start, I would like to just make a remark that it's been a bit less than 2 years now that I'm not doing category theory as my everyday life. So I'm going to present a paper which has been recently published, but for which I had the results already quite a long time ago, and that I presented in CT 2021 already. So nothing changed much since that talk. And so what is going to interest us in this talk is the following very vague question, is that we are going to look for classes of morphism that behave in the same way as surjections do in the category of sets and functions. And to be a little bit more precise, we are in the context of a finitely complete category, and we are looking for classes of morphisms that interact with finite limits exactly in the same way as the class of surjection interact with finite limits in the category set. And before making the question even more precise and perfectly precise, I'm going to try to give some example, or I would say some tentative examples, and see what fails. So the first idea one came up with is the idea of epimorphisms, since we know that in set, surjection can be described as epimorphisms. So basically, morphism for which we have a right cancellation property. But as we know, this is not a very good solution for a problem because, for example, in the category so of monoids, the inclusion of natural numbers into integers is an AP. And in the same way, if we look at the category of rings, we have the inclusion of integers into rational numbers, which is also an epimorphism. And so in those categories, we have a mono, which is an AP. And this is not something that can happen with surjections in the category of sets. And therefore, we want to avoid this phenomenon. And so as a first property, we're going to ask that the class E does not contain any proper monomorphisms. So in other words, all mono in E should be isomorphs. And therefore, the class of epimorphism is not going to be a solution to the problem I posed at the beginning. Okay, so if epimorphisms do not work, maybe let's try regular epimorphisms, because again, in set, surjection can be described as regular APs. So recall that a regular AP is just a co-equalizer of some pair of morphisms, or co-equalizer of its kernel pair. And the good thing with regular APs, first of all, is that in all algebraic categories, regular APs are exactly the surjective homomorphisms. And moreover, they satisfy the first criteria, namely that a mono, which is a regular AP, is automatically an iso. But in some category, for example, in CAT, the category of small categories and functors, regular APs are not closed on the composition. So you can find two regular APs for which the composition is not a regular AP. Something that cannot happen with surjections, of course. And therefore, we're going to ask a second property for E is that it's closed on the composition. And so the class of regular AP is not going to be a solution to a problem neither. Okay, so AP and reg AP do not work. What about strong epimorphisms? Because again, surjection can be described as strong epis. So recall that an epi is strong if in all squares, like here, where the bottom morphism is a mono. So E is strong if only if there exists a unique diagonal filling for all these squares. And this can be described equivalently as extremal epimorphisms. So these are EPs which do not factorize through any proper monomorphism. Okay, so in set and in any algebraic category, strong EPs are exactly the surjective homomorphisms. And moreover, strong EPs satisfy the first two properties, namely that they are closed under composition, and any mono which is a strong EP is an iso. However, they do not satisfy the following property. Again, a counterexample can be found in cat, is that they are not stable under pullbacks. You can indeed find in cat a strong EP for which one of its pullback is not a strong EP anymore. And since it's a property about the class of EP and finite limit, and since this property holds for surjection in set, we want this property. So we want that E is stable under pullbacks, and therefore the class of strong epimorphism is not going to be a solution to a problem. Okay, so I presented already 3 counterexamples to the problem, namely EP, regular EP, and strong EPs, and with them 3 properties that the class E should satisfy. So now let me make the problem absolutely precise. And basically, I'm going to formulate the problem through an embedding theorem. And basically, what I would like is that is to be able to embed C in a pre-sheaf category via a functor phi, such that the following 2 properties are satisfied. So the first one says that phi interact well with finite limits, so basically it preserves and reflects them, and it interacts well with the class of AP that are considered. So a morphism is in the class E if only if its image under phi is a component-wise surjection. And you see that we're going to embed in a pre-sheaf category, because in a pre-sheaf category, more or less everything is calculated component-wise, and therefore it behaves exactly like surjections in the category of sets. And why do I say that such a functor is an embedding? Is because simply this implies that phi is faithful and conservative. It reflects isos. I'm also going to talk about a full version of the embedding theorem, namely just to add as an additional condition that phi is full. So this is the formulation of the problem, and I'm immediately going to give the solution to it. And here it is. So we consider a small finitely complete category. So small, just because in all embedding theorem we have some smallness assumption almost every time. And E is a class of morphism. And we have the embedding theorem. So the embedding I just presented, if and only if E satisfies 5 conditions. So the first 3 are already mentioned. So every mono in E is an iso, E is closed under composition, and E is stable under pullbacks. But we also want to avoid trivial examples. The first one is the empty class. So to avoid empty class, we need that E contains all identities. But this is not enough, because here E could be just a class of isos. So we need to add the last property, is that E has a strong right cancellation property. Namely, if the composition of G after F is in E, is in the class, then G is already in the class E. So basically this describes the embedding theorem. So we have an embedding with the mentioned properties, if only if E satisfies those 5 properties. And in that case, I call E a surjection-like class of morphisms. Okay, so this is for the conservative case, and for the full embedding theorem. So if we want to add as an extra condition that the embedding should be fully faithful, then we need a sixth property, namely that any morphism in E is a regular AP. And in that case, we can just forget about the first property because it's going to be implied by the last five. And in that case, I call such a class E a regular surjection-like class of morphisms. Okay, and so as I said, we already have three counter examples to such classes, namely APs, regular APs, and strong APs. So now let me present some examples. And the first easy one is the class of split APs. So namely morphism which admit a section. And this class, we can very easily check that it's a regular surjection-like class of morphism. So namely we have all the properties in the full embedding theorem. And moreover, it's the smallest such because it's included in any surjection-like class of morphism. That's quite immediate to prove because we need identities in the class E, and then we conclude with the strong right cancellation property. Okay, so this is the smallest such, and since it's a regular surjection-like class of morphism, we have a full embedding theorem coming from that. But this full embedding theorem, we know it from a long time because if you take Yoneda embedding, it does the job perfectly. So nothing new here. As a second example, so I say that strong APs are not a solution because they're not stable on a pullback. So what if we consider the closure, the stabilizer, and the pullbacks? And so basically we consider stably strong AP morphisms. So stably strong AP are just morphism for which all the pullbacks are strong APs. And then in general, this class is a surjection-like class of morphism, but not a regular one. For example, in cat, it's not a regular one. And this class is the biggest one. So any surjection-like class of morphism is included in stably strong APs. That's also quite easy to prove. And as far as I know, the conservative embedding theorem coming from that class is new to this work. Okay, so now as a third example, we can see the class of stably regular AP morphisms, which are better known as descent morphisms. So basically, these are morphisms for which all the pullbacks are regular APs. And in general, this is a regular surjection-like class of morphisms. This is quite surprising, what you can think, because as I said, regular APs are not closed under composition, but stably regular APs are. And the proof that this class satisfies all the properties is due to Janidze, Sobral, and Tolan in the 2004 paper. This paper is going to come quite often now in this talk. And this class is the biggest regular surjection-like class of morphisms because any other one is included in that one. And since it's a regular surjection-like class of morphisms, we have a full embedding theorem coming from that one. But this full embedding theorem is already known. It has been proved by Barr in 1973. And this is basically a corollary of this embedding theorem for regular categories. So we can see the theorem I'm presenting now as a generalization of Barr's embedding theorem for descent morphism, which itself is a generalization of his own theorem for regular categories. And as a fourth example, I can cite the class of effective descent morphisms. It's also a regular surjection-like class of morphisms. And the proof is not easy. So, okay, the first property that it contains identities, that's quite obvious. The fact that all morphisms So all effective descent morphism is a regular EP. It's almost by definition. But then it has been proved by Manuela Sobral and Walter Tolan in 1992 that this class is stable on the pullbacks. It has been proved by Retterman, Sobral, and Tolan in 1993 that it's closed on the composition. And again, in the 2004 paper by Janidze, Sobral, and Tolan, that it has the strong right cancellation property. And here in this last proof, I would say is really not trivial proof, and more it uses some smallest assumption on the class on the category C to embed it somewhere to have to make it easier. And I've never seen a direct proof of this fact, which doesn't use the smallest assumption. So yeah, this is a non-trivial fact that this class satisfies the 5 properties we need. And since it's a regular surjection-like class of morphism, we have a full embedding theorem, which again I think is new to this work. Okay, so that's for 4 general examples. So now let me just study a bit more carefully the category cat of categories and functors, where we have infinitely many examples back. So for n, a natural number, I'm going to call En the class of functors which are surjective on n composable morphisms. So for each sequence of n composable morphism in the codomain category, the property is that they exist n composable morphisms in the domain category which are mapped to the given one in the codomain. Okay, and so we have inclusion, so E0 contains E1, contains E2, and so on and so forth. And all these inclusions are strict inclusions. So E0, we can just see it as the class of functors which are surjective on objects, and it's not a surjection-like class of morphism, just because it contains proper monomorphisms. Okay, E1 is well known, is the class of stably strong EPs. This has been proved by Bernardsky, Borsiskovsky, and Pavlovsky in 1999. And this is not a regular surjection-like class of morphism. This is just a simple surjection-like class. So therefore, we have a conservative embedding theorem, but not a full one. So the class so from E2, so E2, E3, and so on, they are all regular ones, so regular surjection-like class of morphisms. So we always have a full embedding theorem. And the class E2 is the class of descent morphisms. This has been proved by the same authors. And the class E3 is the class of effective descent morphisms, again by Janidze, Sobral, and Tolan in 2004. So this gives infinitely many examples of a regular surjection-like class of morphisms. But there are still more in cat, because you can, for example, consider the intersection of all of them. Again, that's a regular surjection-like class of morphisms. And it strictly contains the class of split EPs, which is another one. Okay, so we have infinitely many examples there. So now let me say a word about the proof of this embedding theorem. So there is one direction which is very easy, namely if we have the embedding, then E satisfies the condition. That's just basically because surjection satisfies those properties. And so component-wise surjection in a pre-sheaf category, they satisfy them as well. And so since the embedding preserves and reflects everything we want, then there is, then the proof is done, basically. The hat direction is the other one, but here is a half-page proof, basically, because we can just consider first Yoneda embedding into the pre-sheaf category, and then the class of morphism E induce a topology on C, and so we can consider the category of sheaves, and we have a sheafification functor from pre-sheaf to sheaves. And then, since the category of sheaves is a regular category, so it's a topos and therefore regular category, we can apply Barr's embedding theorem to have the embedding in a pre-sheaf category. And the composition of these three morphisms, so these three embeddings, they satisfy the properties we want. So this could stand as a half-fledged proof of the theorem, but I don't really like this proof for the following reasons. And the most important one is the fact that even if C is considered a small category, there is still a size problem there, because the category of sheaves is not small, even if C is. And so technically you cannot apply Barr's embedding here. We can still agree, okay, let's change universe, make the category of sheaves small, and it works. Okay. First of all, not all people will be happy with that proof. And secondly, the category of pre-sheaves we have here, so the category of, basically the category of sets here, will not be the usual one, but will be a bigger one. So it's not going to be the category of sets for the universe we are considering. So there is still something not really nice here. But so if you care about size, then you should not be happy with this proof. But also, even if you don't care about size, you have no idea of the construction of the embedding here. It's really obscure. It's just, okay, unidaire, we know it very well. Sheafification, the description is not like, okay, it's still understandable and we know it, but it's quite difficult. But Barr's embedding on top of it, we have no idea how to describe this embedding. And moreover, it uses transfinite inductions. And I know that in the community, this raises some concerns about the validity of the theorem because it uses transfinite induction. And moreover, since we have no description of it, it's going to be difficult to generalize the theorem if we want in a future work, for example, to go from class of morphisms to a class of co-spans. We have no clue how to do it with such a proof. So instead, I choose another approach, which works if, as soon as C is small, this is going to work. So there is absolutely no size issues. And I have an explicit description of the embedding. It's a long description, I agree, but it's explicit, nothing hidden there. And it does not rely on transfinite induction. So just classical induction, no transfinite ones. So basically the concerns that the community has with the transfinite induction in Barr's proof now vanishes because this provides a proof in particular of Barr's embedding theorem that doesn't use transfinite induction. And the proof is largely inspired by Barr's embedding proof. So the proof of his embedding theorem for regular categories. So basically what he does is to embed C in the pro-completion and do some construction with limits and colimits, which are not easily described as an element of C. And basically, the proof I did is to express everything in terms of C, and so everything was explicit. And it gives rise to a kind of long proof. So in the published version of the paper, it's 51 pages. But I claim that any student that follows a first course in category theory should be able to understand it if he has time to spend on it, because it's just about functors which preserve finite limits, basically. And if you know this concept, then you can follow the proof. And therefore, since we have an explicit description of the embedding, maybe it can be possible to generalize it to classes of co-spans. So it's for future work, or should I say for future life. Okay, so since I claim that there is an explicit description of the embedding, let me give it, or at least some part of it, because it's very long. And I'm just going to focus on the conservative embedding. So in the conservative embedding, we first need to construct the category of pre-sheaves, so the category D here. And the category D has the same objects as C. Very easy. For the morphisms, it's a bit harder. Basically, for each object of D, you associate a functor, and the morphism are just the natural transformation between those functors. Okay, and now the embedding itself, how to describe it? Well, if you have an object C in C, so phi of C is just a pre-sheaf. To describe this pre-sheaf, you evaluate at D, another object. And this set is a quotient. I'm not going to describe the equivalence relation, but it's a quotient of the set of those finite diagrams where we have a tower of pullbacks, and where on the bottom left you have the object D, and on the top here you have the object C, and on the right you have morphisms which are in the class E and which are part of the structure. Okay, so this gives an idea of the construction, and I would like to conclude by giving two applications of this embedding theorem. And the first one is more philosophical, because it gives, I mean, in my opinion, is the most important one, is that this embedding theorem gives some criteria to which classes of APs to choose once we just interest in finite limits and good APs. And if we just interest into those, I think that this list of axioms gives some good choices for the class to work with, or maybe just to work with a general class of APs that satisfies those properties, because very often it's going to be enough. And by that, I also mean that if we are not interested, or if we don't need factorization when we play with regular categories, so the regular AP mono factorization, then most probably we are able to generalize it from regular categories to finitely complete categories, and where we will place regular APs by just a general class of APs E that satisfies those properties. And the second application of the embedding theorem, and I'm going to conclude by that, it's a more concrete application, is because now we can prove theorems which are about finite limits and good APs, just using elements as if we were in the category sets. How to do? So to explain that, I'm going to give an example with Bar-Cock theorem. So let's suppose we have finitely complete category C and a good class of APs, so just a surjection-like class of morphisms. And we have this diagram here where E is in the class E, and here R1, R2 is a kernel pair of E, and S1, S2 is a kernel pair of F, and one of the square here, it's a pullback, and we would like to prove that the square on the right is a pullback as well. How to do? Well, first we invoke the embedding theorem. Firstly, we can assume that C is small if we care about sizes just by changing universe, for example. So we have an embedding, and then we're going to use it. So we have this situation in C. We apply the embedding phi everywhere. So we have this situation in the pre-sheaf category, where all limit conditions are satisfied again. So the pullback and the kernel pair condition stay true because phi preserves limits. And phi of E is a component-wise surjection in the category of pre-sheaves. And since in that category of pre-sheaves, everything is computed component-wise, we can evaluate it at some component, just a random component, so a random object of V. And basically, we have this situation now in set, and just also keeping all limits properties because limits are computed component-wise. And now phi of E of X is just a surjection. And now we can just prove Bar-Cock theorem just using elements as if we were in set. And this means that we have a pullback in set here on the right. But since in the pre-sheaf category, pullbacks again are computed component-wise, we have a pullback here on the right in the category of pre-sheaves. And finally, since phi reflects finite limits, we have a pullback in C. And that's it. So I'm going to conclude here. Thank you very much.
Thank you, Pierre-Alain. Thank you very much for your very interesting talk. And we have a few minutes for some questions, if any. Just unmute yourself and ask. Or comments or any.
Maybe can I ask a question? Hi, can you hear me, Pierre-Alain?
Sure, yes.
This technique of proving things by reducing it to sets, those two embeddings into sheaves and then applying bar. I know that there is size issue, but we could still use those to make the same application, right?
Yes. If yes, if we use now twice the maximum of universe, basically. So yeah, if you don't care about sizes, yes, perfectly.
No, I absolutely appreciate the fact that you've been able to reduce this to small situation. I think that's fantastic. And the second question is, I think we've talked about this before. So one might say, okay, a nice notion is growth-unique topology, and a nice class of epi should be the one that forms a growth-unique topology, and then the answer would actually be exactly what you have, except this condition that about the mono part, and that's reflected in the fact that you're able to do sheavification.
Yes.
It's just a comment.
Yeah.
Thank you very much. Very nice talk.
Thank you.
Thank you, Zura, for your question. Thank you, Pierre-Alain. Any other question or comments? By the way, Zura was asking on the chat about the recordings, and they will be made available as soon as possible on the Ithaca website. Yes, and all other talks given in the past are already there. So sorry. So any other question?
If I can, I have a question.
Yes, of course, Enrico, please.
Okay. First of all, thank you, Pierre-Alain, for your talk. If I'm right, you said that your proof is somehow inspired from bar embedding, from the proof of bar embedding theorem.
Yes.
But in your proof, you don't use transfinite induction when bar use it. And so my question is, there is some hope to get to go in the other way. I mean, to get a proof of the bar embedding theorem without using transfinite induction.
So first of all, the proof I gave by corollary is just a proof of bar embedding theorem without transfinite induction, but I would say a long proof of it. If we want a short proof by using the same technique as bar, I don't think there is a hope, because basically using just covering over and over of some object and then take the limit of it and repeating again and again using like a small object argument, basically. So it's just a transfinite induction on those things. And since it doesn't have some explicit description of this limit it takes, I don't see how we can avoid the transfinite induction. Since, in opposite, in my case, I have an explicit description, so the transfinite thing just vanishes by itself because I have the explicit description, so there is no difficulty to go to the limit step, I would say.
Okay, thank you.
Thanks.
So let's thank Pierre-Alain again. And thank you.
Thanks to you.
And so we are switching to the next speaker, which is Manuel Mancini.
Hi to everyone. Do you hear me?